All right, so we'll be going through CH120, CH110. The content is just similar, and you are free to go through the paper, stuff like that. Just for revision, you people are writing exams, and I'm wishing you all the best as we are revising with this paper. So, um, let me show you the overall like content that we have in this paper. I've picked those important questions such as Bronsted, Lewis base, stuff like that. We have conjugate stuff like that. Then we have the properties cave strong acid, stuff like that. So we have dissociation stuff like that. We'll be able to do all these, calculating the Kc, okay, that is the chemical equilibrium. Also this under chemical equilibrium, we have also again chemical equilibrium. We have this one. Where is this topic coming from? Oxidation, stuff like that, reduction, stuff like that. We have acidic, basic media will be able to balance. So we have a long way to go. We need to show also the bronze thought. I mean the graph, Cass's graph. Then we end there. All right, we end there. So that's our content. Otherwise, pay attention and learn something new with us. Okay, sure. So now we are starting now. Question one. I'll be very fast because some of the things like we learned them. So I'll be very fast. Okay. So briefly distinguish between an acid and a base by completing the table below. So Um, when you say the definition of acid according to Arrhenius, arrhene is to produce something. That's the meaning of arrhene. The word just arrhene is arrhene is to what? To produce something. Okay, so by that you can master it by say this one will produce positive hydrogen ion. So it produce positively just hydrogen ion. It's enough. Okay, this one produce what? It's the opposite. Produce hydroxide. All right. Hydroxide. How do you write hydroxide? It should be negatively charged, right? So write negative charge there. It's an ion, please. In water, and they produce all these in water. So you can say in water if you want. So bronze state law also. Bronze state law, this one defined an acid as a proton donor, okay, or a substance that donates a proton. A proton, by this case, we mean a hydrogen ion, okay. So this is the proton. That's how he defined this guy, proton donor, okay. That's what he said. It's a proton donor. Then this one is a proton acceptor, okay. That's how he defined like a base. So Lewis now an acid. Lewis defined an acid as. By the way, Lewis defined a base as something that has lone pairs. Okay, like for this one. Okay, so that means these two electrons that are there, they are electron pairs. So he defined an acid as. Lewis defined an acid as um an acid is something that accept electron pair. Okay, accept. Wait, let me rub this. Something that accept electron pair is called um. It's called an acid according to this guy, Lewis guy. Okay, so that's how he defined an acid. He said electron pair acceptor. Okay, so electron pair, electron lone pair. Yeah, those things they are called lone pair. Lone pair acceptor. Okay, this one is electron lone pair donor. Okay, so this one donate electrons. Okay, electron pair. Okay, so that's about this guy. That's how they defined these acids. So it's very important that you understand these two. Okay. All right. It's important that you understand these two. All right. I mean, these three guys, they are used in defining this, and they will ask you one day. So it's better you explain it. So the other thing is, uh, given the conjugate acid for each of the following. So these are acids. Now give the conjugate acid for each of the following bases. So these are bases. So we need to give. So by the way, there's a negative there. Okay, and also there's a negative there that you can't see. Even there's a negative. Okay. So now we are asked to actually to give the conjugate acid. Acid, you add the hydrogen. So how do you do this? You add hydrogen. Hydrogen, you add the hydrogen ion. So when you add hydrogen, it will neutralize. So the negative and positive will cancel. So we just will remain with the hydrobromine just like that. That's our conjugate acid. Even here, since now it's nothing is zero there, and we are bringing this guy there, so it will be attached to the friend's hydrogen there. So the conjugate acid will be there before, then there will be plus, because we have brought something that was positive. You see, it's more like we have A positive, okay, reacting with something B. So AB will look like this, okay. It will also have B as the overall charge. So that's what will be here. So we need to put a plus because of the plus, just to balance the plus that we had from the hydrogen. Okay. So by the way, hydrogen will go to C to the friends. Here it's C negative. So that will be cancelled with the hydrogen positive ion. So there will be our molecule. By this is just I. It's not so that will be our conjugate acid. Then here also it was negative 2 there. So it will be negative 1. So we attach hydrogen, and the hydrogen, it will cancel like that, and it will be negative 1 because of hydrogen which was positive. So the other one negative has gone with that, and they have cancelled, and it remained with this negative. So that's how we balance this. These are the answers you needed to put. Okay, so hope you are getting there. So that's how to find the conjugate. Even here we will see now to find the conjugate. Classify each of the following as Lewis base acid and stuff like that. Like I said, a Lewis acid, I mean a Lewis base, will have something like, I like giving ammonia. Whenever they are lone pairs, just know that that thing is actually a base, Lewis base, because it's an electron pair donor. Okay. So here, if we were to draw the structure of water, okay, so water will look like this. By the way, there are two electrons there for water, because what we do is we get two electrons. It's coming from group what? One. So you get one there. It's coming from group what? Is it? Here it's two because of two hydrogen there. Then here it's coming from group 6. So we're having 8 electrons, and we have two there, right? Making 4. 4, 5, 6. Is it making sense? Oxygen. Where is oxygen coming from? Okay, it should be group 6. Group 6 plus 2 from hydrogen, that's making 8. Okay, so meaning the other 2 electrons there. So in short, by the presence of these two, if you are to draw the structure, Lewis structure like that, then you need to see the electrons. Once you're able to see these extra electrons, then that just know that it's a Lewis base or Lewis acid. So for this one, it will be a Lewis base because I demonstrated the electrons that remains. We said there we get 2 times what is the valence outermost shell of hydrogen? It's 1. Then there it's what is there? It's 6 times 1, getting us 8 total. Okay, so it means we have used the 2 electrons there, 2 electrons remaining with what? 4. So I think the 4 will sit there. Okay, that is if I'm not mistaken. But the presence of hydrogen, this is the one which should tell you that okay, this is a base. So in short, water is a Lewis base. Okay, because of those presence of what? So this is a base, a Lewis base. Okay, then coming to this one, which be a Lewis acid or Lewis base? What will be this? Also, this is ammonia which I've been talking about. This will be definitely a base. a Lewis base. So coming to this, the way it is arranged like this, boron, is it coming from, I don't know the group where it's coming, but this one, um oh, I remember for this one, let me just show you something. I mean for, I'm sorry for here, for boron. Boron, the electrons, there is no lone pair in boron, so it sits like this. Okay, it's trigonal. So what will happen is we have F there, okay, even there F, even there F. So this is coming from group O. This is should be group O, if I'm not mistaken. What is the group for boron? Should be 4. I don't have a periodic table with me. SA is 4. There it's C. Um, boron, is it not 7? I'm not really sure, but the electrons, there will be no extra electrons. So this is on this central atom, there will be no extra electrons, just like this. So that means, that proves to say this guy is actually doesn't have anything there as electron. So that will be a Lewis what? Acid. Okay, it will be Lewis acid. Why? Because there is no lone pair. Your goal is to look at lone pairs, draw the Lewis structure, and you'll be able to do this. So know how to draw the Lewis structure. So if I'm to draw the Lewis structure, I've shown you how to do it. So this I'm saying is an acid. Then this one we can see it doesn't have electrons. Only what it has is what? That positive, of which the presence of an acid. Okay. So that is it about this one. Sure. Okay, briefly distinguish between a strong and weak acid by completing the table. There was a table that I've forgotten, but what you need to know is that a strong acid actually ionizes completely. This one partially ionizes in water. Okay, that is it. So that is it. A strong acid completely ionizes in water. If we had, let's say, this is an acid, okay. Um, let me do this. Sulfate. Let me just write sulfate. So if it's to ionize it to give hydrogen to there, then plus sulfate like that. Okay. This is completely, so it's strong. But if it is weak, it will ionize like this. Okay. So it can even be like this. It can be at equilibrium because it can go back to this. But this one is irreversible because the hydrogen has been given off. So we have hydrogen plus hydrogen sulfate like that. So that means this is weak, this is completely, which is a strong acid, this is a weak acid. So that's how you can actually distinguish the strong and the weak acid. So I left the diagram when I was typing these questions. Okay. So now what we are trying to say now is um um so we have what we call K value for strong acid and for weak acid. So for the K value for strong acid, it will really be very large. Okay. Why? Because if something is able to ionize completely like that, okay. If something is able to ionize like that, meaning we have a good Kp value there. Okay. The product will be a lot, like because it's completely okay. Because what you need to know is that this K values of an acid, it means Ka, it means an acid, Kb means a base. So if it is given by, let's say, Ka is equals to the ionization of the product that has been formed, product of a reactant. Okay, so if we have more of ionizing products, it means we have less number of what? Reactant. And let's say we have 2 there, then here we have 1. We will have the K value 2, meaning that the K value will be very large if something is ionizing completely, like from the above statement. So a weak one will have a small what? Small K value, Ka. Okay, here Ka is big. Position of dissociation equilibrium, what will happen is that since now the position we have a lot of them, right? We have a lot of products for strong. So it means we are forming more of, we are reacting A plus B to give C plus D. So if we have very strong, of which it will is very strong like that, it means we'll have more product. You've seen, and the position, it will shift. Okay, I mean, first, just at start, the position will go to the light because we have a lot of what reaction. In short, the position of dissociation, the position goes like this because it want to dissociate, it want to break. The breaking will go right. You get? That is it. Then for this one, it will go left, the breaking, because it can go double like that. So if it is weak, it means the breaking will be, in fact, partial like that, like that. But for this one, the breaking will be just direct. Let's say it will go direct to what? To what is formed, hydrogen plus chlorine. That's what will happen for strong acid. Then hydrogen ion equilibrium concentration compared with original. So here, what will happen that this hydrogen for strong acid, it can be equal to of that acid. Okay, meaning that it is very strong. We are looking at hydrogen concentration. It will be very strong as same as to that acid, but here the hydrogen concentration produced is less than that of acid. Okay, so that's how we differentiate the two. Then strength of conjugate base compared with the basic strength of water. So here it will be weak. This is opposite now. For strong acid, this, because we are conjugating something now, a base. So the base that will be there, it will be weak because it has been more of diluted or changed from that strong acid to a base. So it will be very weak, weak than water. Okay. Then here it will be strong than water. That's what will happen. Once you conjugalize something, you have reduced the power. It's more like you are doing transgender to something, and someone, a female, a guy who has gone transgender, they have changed their gender. So that means they'll be very weak. Yeah, because girls, they are not that strong as compared to guys. So you are changing something. So even them, they will change just like that. Okay, briefly explain the terms monoprotic, diprotic, and the triprotic acids and give examples. So, a monoprotic acid is an acid that donate one proton, okay? One proton or hydrogen ion. That's what I mean when we say proton, okay? We mean this guy, okay? That's an ion proton here in chemistry. So, what will happen is that if an acid is a mono, it means it gives only one hydrogen. For example, I'm giving you an example, I'm answering. So monoprotic, we have, let's say, chlorine, I mean hydrochloric acid, because of this hydrogen there, okay? That's monoprotic, it gives one proton. Then diprotic, we can say sulfuric. So it gives what? Two, okay? Proton. Then triprotic, we can try phosphoric acid, 3 there, then sulfate, 4. So this gives 3. Have you seen? So I've given the example, and also you define to say this is an acid that gives 3 protons or donate 3 protons. Okay, so that's how you actually attempt this. Okay, so that's about this one. So we go to the next one. Using the equilibrium, using the equation. So we are using this equation now. Okay, so using this equation, now, we want to derive the expression that we can use to calculate Kc and the Kp value. So okay, so Kc will be given as the product concentration, this C means concentration, over the reactant concentration. So we'll say the product concentration. Concentration in these brackets mean concentration. So I'll put C, okay? Then you put the power, this actually balancing number, more ratios. Then also D, okay? Then to the power D over the same A now to the power A, raised to the power A, okay? Then again B raised to the power B, like that. So that is what? That is the K what? Kc, concentration equilibrium. Then also Kp, it will be given as, all right? Kp also will be given as the partial pressure of A, okay? Of C, I mean. Okay, this one we don't put those curly brackets, we put these normal brackets. So again, raised to the power C, again the partial pressure of D, okay? Raised to the power D, again the partial pressure of, it is expressed in terms of pressure, partial pressure. So we have partial pressure of A to the power A. Again, we have partial pressure of what? Partial pressure of B to the power B, like that. Okay. So these are the two concentration equilibrium expression. When you say expression, you mean an equation just. Okay. That would have been used. So at 20 degrees Celsius, the vapor pressure of water is this one. Calculate the Kp and the Kc value for the reaction. Okay. So here, using these, you've seen these. So there's a relationship between these two guys. Okay, there's a relationship between these two guys. It's given as Kp, it's given as Kp is equals to Kc, okay? Then RT, okay? Then change in number of moles. So this is the expression that is given, that govern the two. So now that we have Kp, it's here. They have already said the vapor pressure of water. Water is already here. So this is the vapor pressure. This is the pressure it has. So Kp will be given as, so Kp in short for this one, they have already simplified. There's nothing to stress. And Kp, just know that is always expressed in what? In 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 gases, not liquids like this. So anyway, I'll come to that. So the Kp value now is 0.0231, like that. Okay. So this is the Kp, but it's a value whereby you don't put the units. Okay. Because everything has been cancelled in terms of ratios. So that's a Kp. Calculate the Kp done. Then Kc, we use now the governing equation to say Kp is equal to Kc, then RT, okay? Then change in the number of moles. Change in the number of moles, we mean product minus reactant. So here we have this one, right? So I can say I can divide throughout by RT, change in moles, even the RT, change in moles. Okay, so that means this goes, so we say Kc is equal to, okay, Kp over RT, okay, then change in moles. Okay, so this means that the Kp is 0.2, okay, to 0.231 over RT, the pressure that we have now, we have to multiply to add this 25. Okay, so we have to add this 20 degrees, we take it into Kelvin. So we say 273 plus 20. Okay, we're getting Kelvin temperature as this plus that. That is 290 something. Okay, so that will be 0 plus that 293. It's giving me 290. It should be 298. Okay, okay, 293. Just like this. So this is the Kelvin temperature. So it's a temperature that I'll put there. 293 times, we have now the value of R. We always use 0.0. Okay, what is the value for, what is the value we use? I've forgotten. Okay, let me think about it. It's 0.028. No, it's 0.082. Okay, 0.0.82 it should be that gas value, the value of R. Let me think about it. Okay, let me think about it. I'm forgetting the value of why is it like this? I'm forgetting it. So let me write the expression properly now. Record. So we write the expression to say Kc, okay, is equal to 0 point, which is Kp, okay, 0 point, okay, 0.0231 over, okay. Then the value of T, like I said, we had put 293, okay, Kelvin, then times, remember first before that, we need the change in moles, this value, this power that I've been writing, this N, change in moles. So that one will be gotten by saying we subtract product moles minus, reactant moles minus product moles. So here we have 1 and also have 1, but this is a liquid, so we don't include liquid. So say just a 1 minus 0. It means here we have 0. Okay. So if we have 0 there, then what will be the change in moles? If you have 0 there, what will be the change in moles? So this means that the change in moles will be just the same one, right? Because there's nothing we can do from there. There's nothing you can do. Okay. So we'll say once we subtract there, we say 1. Okay, moles. So the change in moles is actually that 1 we have there. All right. Okay. Let me just change the pen. Just change the color, the pen. Just a moment. I'm changing the. Okay. Okay, so so that's a change in moles that I'll put. Anyway, I've forgotten. I said this is 0.0821 mostly, then change in moles is just 1. So when you punch that on your calculator, okay, you're going to find that Kc is 9 point, let me punch, okay, 9.6 1 times 10 to the power negative 4. Okay, so that will be our Kc value. Okay, here is now another animal. Calculate the equilibrium concentration of tricro is it trichlorophosphorus, then dissociating into chloride, and the initial concentration of pentachloride is this one. So here we would have done this, would have used the IC table, but I'm seeing some data missing. See, calculate the equilibrium concentration of this one dissociating, so of this one. So say pentachloride phosphorus, because of penta 5 there, okay, 5, then this dissociating into trichloride phosphorus, okay, giving us, plus chloride, like that. Okay, it's balanced now. So here what we needed the concentration at least for one of these guys, such that we use the IC table, okay, whereby we could put the concentration initial, most of these are given 0, then the change, okay, here it's always negative, then here it's always plus positive, then we subtract, this will be 1, that concentration minus x, okay, then here you have x, then here you have also x when you add, then meaning that the Kc would have been the concentration of this one and 2, it will be x times x on top, then over the change, which is 1 minus x. Then would have done, because we have the K value, and would have found the value of x. This would have been squared and would have found the value of what? The value of the other guy, which is the equilibrium concentrations of the two. Okay, so we don't know the concentration of the source. Okay, so we won't do anything for this one. Instead, that's just the hint you should be using. Otherwise, we would have used even a quadratic there. Let's see this one. Let me see this one. What would be the effect of position, equilibrium, and value of equilibrium? Okay, constant Kc. If the temperature, so when you increase the temperature, suppose we have A plus B, okay, forming C plus D. Okay, so at equilibrium, this is equal. Okay, at equilibrium, that is equal. Product forming is equal to reactant forming. So a temperature is increased. Once a temperature is increased, we increase in the vessels, in the test tube, meaning more product will be what? Formed, right? Yes. More product will be formed, okay? Then it means more product will be formed, then the Kc value will also increase, because let's say we have 3 over, we had 1 moles of reactant, meaning more products are increased, meaning that the Kc will go up. So here, temperature will shift to, it will cause to shift to the right, and the Kc will increase. That's the explanation you should give here. I'm just writing it, but get the knowledge I'm giving. Then pressure is increased. When you increase pressure, you increase the number of moles, like that. These are things involved for those that are in gases. So when you increase the pressure, it means you have reduced the volume. Okay. So if you increase here, there were a lot of you increase the pressure here. Okay. So it will go where there are few number of moles. Okay. If you had 3 there and again 3 there, then 1 there, 1 there. So it means the pressure is increased this side, so the equilibrium will shift like this. So it depends. This one is not specific, okay? It's general. So that's what we mean for this one. And this is just same as reducing the volume. Reducing volume result into what? Increase the pressure. So the effect that is found there is the same effect that is found there. So that is it. Anyway, I'm not writing a lot because of what I'm explaining is enough than what is actually I can write. Yeah, because we have a lot to do. So for this one now, this is where I said we have a lot to do. Okay. At the start of the reaction, there are 0.249 moles of nitrogen, 3.21 times 10 to the power negative 2 moles of hydrogens, and 6.42 moles of ammonia. They were put in 3.50 liters reacting vessels or reaction vessels with the temperature of 375 degrees Celsius. Kc for the production of ammonia is this one. So we have the Kc value at this temperature. So is this system at equilibrium? So what we are going to do, if it is at equilibrium, let us calculate Kc. We calculate K. There is what we call okay. So there are two things that we do here. Okay. Is what we call Kc and Qc. So when you say Qc, it's more like, it's more of product, okay? Then Kc, it's more of reactant. If this Kc is greater than this, it means we have more. If this is greater than this, it means we have more of reactant than product, okay? But this Kc relate more of product, okay? I mean Qc relate of more product. Suppose, so this I said relate this Qc as of this product, then Kc as reactant, like this. So we have Kc there, right? So what you are going to do is I'm going to calculate, okay, this Kc is same as Kp at equilibrium. So if they are equal, it means the reaction was at equilibrium. So they have given us already what? Kc. So I'm going to calculate the Qc, meaning that if they are equal, it means the reaction is at what? At equilibrium. Okay. So we'll see that how we can do that. Okay. So that is it. So what we are going to do is we are saying now, so I'm going to calculate Qc. They use the same formula. Okay. The product minus, so say the product concentration over reactant concentration. Okay. So, but the concentration we don't have, we only have moles that they were put in one vessel. So we divide every moles with this value to get their concentration. Okay. So for nitrogen, we'll say the moles that were given for nitrogen is 0.249 over the same 3.50 liters to get the concentration. Okay. Then also for hydrogen, I'll do the same. We'll say 3.21 times 10 to the power negative 2. Okay. Divide by the same 3.50. Okay. Then for ammonia also, let me write for ammonia here. Okay, the ammonia formed. By the way, the reaction that was supposed to be performed is, this is how you write the Haber process reaction, or just the formation of ammonia from hydrogen and the nitrogen. So this will form, by the way, it's equilibrium concentration. You can write two arrows, but I prefer writing like this. So to balance it, I'll write with 2 there to balance everything. Okay, so that will be nitrogen 3, like that. So that's how you light the reaction. So this is the reaction that we even govern. So now you can see we have 6 number of hydrogen. So I'll put 3 there. Okay, so now my reaction is balanced. So now I'm calculating this also for ammonia. For ammonia, we have how many number of, we have 6.42 times 10 to the power 34 over, okay, over 3.50 liters. We are getting now, remember we're dividing moles over volume, okay, moles over volume, okay, even their volume. So that's what I'm getting is concentrations. So here the concentration will be for ammonia, it will be, when you punch that on your calculator, it's giving me one, is this 1.3 times 10, okay, to the power negative 4. Then I'll come back to this space. That's where I'll find my value. So then for nitrogen, the concentration that I'm getting is 0.009174. Okay, no, just 7. All right, so that is the concentration I'm getting. Then for hydrogen, I'm getting I think I've calculated already for hydrogen. I've calculated for nitrogen, it's 1 point, for ammonia is 1 point. So for hydrogen, no, I've made a mistake. I need to punch this properly. I'm not sure. So I don't believe this. Okay, so when we punch for nitrogen, we are getting 0. 0.071. Okay, 1. Then here we are getting, when I punch that, we are getting 0.00917 m, like that, or concentration moles, I mean in moles per volume. Okay, this is the concentration. So now this space that I have kept here is the space now that I'm going to use now. So say QC, okay, is it's called equilibrium quotient. So what I'm going to do is I'll say product from the reaction is what? Just ammonia. Okay, you write that, you raise to the power 2 over the reactant. We have nitrogen there, nitrogen 2 to the power 1, because then we have hydrogen there to the power 3 there. Okay, we substitute those values. For nitrogen, we have what? That value. So say it raised to the power 2, so have 1.83 times 10 to the power negative 4, open bracket, to the power what? 2 there. Okay, then here we have for nitrogen of 0.0711. This is not raised to the n power, right? By the way, you put these curly brackets, for concentration. Then we have also for hydrogen now. Hydrogen we have 0.00917. Then raised to the what? The power 3 from the given balance equation. So raised to the power 3 like that. So when you punch that on your calculator, so when I punch here, I'm getting 0.56, 0.56. Okay, this is the value I'm getting. So this is the Kc value. Okay, so is Kc value equal to what? To so is Kc equal to QC? That's my question. The answer is no. So this means that the equation is not, I mean, the equilibrium, the system is not at equilibrium unless if they were equal. Now that which one is big? I said this is more of product, this is more of reactant. So if which one is big here? Which one is big? Okay, we can see this one is big, this is 0 point. Kc is, so we are saying now Kc, okay, is what is greater than QC. Okay, this means that we have more of reactant than products. So this means that the reaction will shift where? Where will reaction shift? Right, it will go and consume more product. I mean, make more product because it has a lot of what? Reactant. So it will go there to form more products. So that's to be the direction. It will proceed in that way. Hope it's clear. So this is where there's wake. And so from third, this is now 0, 1. Anyway, we continue. So what we do is now for this one, what we are going to do is we are going to calculate the oxidation state of each. So what you do is you get this element. So you say, I will say X, okay? This guy, it has the charge of what? The valence it has, it's in -2 oxygen. This is the charge of overall this thing. So the overall compound has a charge of -1. Then oxygen inside there, it carries the valence of -2. You all know that. So we say X of that element we are looking, then plus that for oxygen times its valence. Okay, everything is equated to -1, the charge. So that will be X minus 8, okay, is equals to -1. So this is -8. When it goes there, it will be X is equals to -1 plus 8, right? That will be X is equals to plus 7. So here the oxidation state is 7. Then for this one, so this is for number 1. Then for number 2, chlorine 2, okay, then oxygen 7, 2, then valence like that. So this means that we have 2 of them. So I'll say 2x, okay, then plus oxygen has been having -2, like I said. So I'll say 7 times -2. Then the overall compound is equated to -2. Okay, so say 2x, that will give us -14 once we multiply there. Okay, is equals to -2. We cross multiply, that will be, when you take 214 there, it will be positive and it will be positive 12, right? You divide throughout. So x is equals to what? Plus 6. Okay, so the oxidation state here is plus 6. That's how you should calculate this. Just mind the guy, like where they're coming from, their valences, and how you equate the charge of the overall compound. Okay, so this one, it's a very long one, but I'll do it very fast. So balance each of the following equation. So we have, okay, so we need to know whether we need to break into half reactions. First of all, you need to tell whether this is oxidation or this is reduction. So first of all, I'll check whether this one, the way I'm moving the arrow, whether it will be oxidation or reduction. See, I'll need to check here, it's showing it's positive 2. So if I check, I'll need to calculate there. I'll say X minus, okay, 4 times -2 for oxygen, then is equated everything to negative there. Okay, so that means that x plus 8 is equals to, wait, I've really made a big mistake. So we are adding there. So this will be negative, then negative 1 there. So that means x is equals to positive 7. Okay. So from positive 7 to positive 2, that means there was a reduction there, right? So meaning that this is a reduction. Okay. So there's oxidation and reduction. So this is reduction reaction. Then by us identifying that this is reduction, it means this is oxidation reaction. Okay, like that. Okay, so we have identified that. So this means that the stage that we'll get now is, I'll write into half reactions. So writing half reactions. So half reactions. Okay, so we have the first one is oxidation half reaction, of which I need to write like this. I've already identified, so I'll say, all right, negative 2 mn. Okay, 2 plus, then, okay, this is how we'll be moving. Then again for this one we have NO2 minus. You can also verify that it's a reduction. You'll find that the electron have reduced. Okay, so the reaction was at equilibrium. You can put this if you want. So then like that. So it means that now I start balancing. These are half reactions. Okay, you'll be writing those statements. You say breaking into half reactions, you write this. Because of time, I want to do that. Then from there now, we have now seen all this. So the first step is to balance the main species, which are this one and this one. They are all balanced in this case, and also here they are all balanced. Okay. Then the second thing is to balance oxygen by adding water. So suppose on the part where it's lacking the number of oxygen, here we have 4 oxygen. So I'll add 4 H2O. Okay. Then here I'll add this side 4 H2O. Aye, 2. Here we have 3 oxygen, here we have 2. Okay. So here I'll add, let me write this, please. I'm not supposed, let me do it on the next stage, so that I create a space. So for this one, I'll say we add on the part where it's lacking. So we have M oxygen, like that. The reaction is at equilibrium. Okay. So we have 2 plus there. So we said we add on the part where it's lacking. So here I'll add 4 H2O. Have you seen oxygen as balanced and also the 4 I have? Yes, they have balanced. Also this side I'll need to add where it's lacking. Okay. Okay. So I'm adding 1 water molecule to make 3 oxygen. So say H2O. Okay. The reaction is at equilibrium. Then, okay. Like that, I've balanced the oxygen. So the next step that I'm doing now is to add, okay. So we add now hydrogen ions to the part where it's lacking. So for example here, we have how many hydrogens? We have how many? We have how many hydrogens? So we have how many hydrogens? Here we have 0, here we have 8, right? So I'll add 8 hydrogen ions. So I'll say M. Okay. Let me increase the space. So I'll say I'll add M. So I'll say M. I need to write a capital letter that. Mn. Okay, O for like that, negative. So I'm adding hydrogen, which is lacking. There are how many here? If you multiply the hydrogen, there are 8. So I'm adding 8 hydrogen ions. Have you seen? This is ion. Then we continue like that. 2 plus M plus 4 water molecule. So I'm done there. So also this side also I'm adding how many? We have two here, just one hydrogen. I also add the one hydrogen where it's lacking there. So I'll say the equilibrium material, I mean reaction at equilibrium. So we have then plus we had hydrogen. So we have only two hydrogen. So I'll add two hydrogen ion like that. Okay. So from there now, what we are going to do is we balance the number of um in fact, let me not even do that. I wanted to check the balance in the number of electrons. Yes, let me balance the number of electrons. So here, if you can see there's negative there and the positive there. Okay, so the total electrons are about charges. So the total electrons that remains there is 7. Okay, so 7 electrons should be added. Then here it means that okay, let me show you what I'm trying to say. There's negative there, right? And also positive there. There's just one negative there and there's positive there. So that means we have 8 positives and 1 negative. So that gives a total of 7 positives. Then here we have 2 positives. So here we have 2 positives. You have seen? So that means, let me write like this. So that means we need to add more positives on the lot of more electrons more on the, so we have 2 positives on this side. Then this side we have 7. So it means for us to remain with these 2 positives, we can't add it. So we'll bring electrons that will reduce. So we'll say plus how many electrons? 5 electrons. So that 5 electrons which are negative plus positive with negative, it will give us positive 2 like that. You see? This is the last part that we need to do. So that is it. Then also for this part, you have seen we have 1 electron there. We have 1 electron there. Okay. We have 1 electron there. Then this side it's 0. What are you going to do? It must be something. No, it's not 0. Here we have 2 electrons positive, then here negative. So it means we will remain with 1 electron positive. You have seen? What I'm trying to say is if we are to write, we are trying to balance the number of electrons, remember. So this means that we have 1 negative electron there and we have 2 positives. This plus this is giving us positive. So we need 1 more electron to be added there. So we need to add 1 electron there so that we terminate this remaining one. That's all. That's the job we have, and we'll be ready to go. We'll balance our reaction in acidic. Okay, so hope you have gotten what I said. So we said this was 2 positive here like that. So now we are going to add here. So say M N O 4 negative plus 8 hydrogen ion. We said to add how many? We said to add 5, okay? Like that, 5 electrons. Then equal to, here we'll say Mn2 plus 4H. Okay, we are done there. Then even here we'll say NO2 negative plus H2O. We said we'll be adding where? This side, so that we can cancel that. So we'll say then plus 2 hydrogen ion, then plus an electron just, okay? So that is it. We are done. Everything is now okay. So is the deal is now to combine this equation and form one equation. That's all. Okay, so I'll group these 2 equations to say, you have seen this one is having how many electrons? 1. This one is having how many electrons? 5. So this one will need to multiply 5 electrons. So I'll bring them together like this. Okay. Plus 8. Like that. 5 electrons. Okay. The equilibrium is at, the reaction is at equilibrium like that. Then 2 plus 4H2O. Then also let me do this one. Let me bring it like that. Plus H2O. Then plus NO3 negative plus H2 plus like that. So now you interchange the electrons that are variable. This will be multiplied by 1 electron. This will be multiplied by 5 electrons. So that we can balance this 5 and 5, then they will cancel. Okay. So this means that if this is to be multiplied by this 1 electron throughout, that means it will remain the same. Okay. Remain the same. Okay, so they remain the same like that. So this means that we have multiplied. Then the second one, it will be 5. You multiply throughout, okay? Plus, again, 5 H2O. You have seen? Again, 5 H negative. Then there to be 10, right? 10 hydrogens ions. Then plus 5 electrons. You have seen? So these are now, we add these two, okay? If you are to add these, you notice that this one is on the right side and this one is on the left side, so they will cancel. That's all. That's a goal of actually multiplying. It's more like elimination method, okay? Then again, what we subtract is, you have seen there are 10 hydrogens there, then we have 8 there. So it means we remain with the 2 hydrogens there, then the 8 will go. You have seen? So that's how we'll actually simplify it. So this should be my last point. Then you try the second one. Okay. So if I'm to do that one now, what we are going to say is, this has been cancelled. Will remain for only 2 hydrogens on the product part. So here I'll start now arranging it the way it was. So MnO4 negative plus, I'll write this if I want, 5NO2 negative plus these 5 water molecules, okay, 5H2. Remember, this has been cancelled with this and remaining with the 2, only 2 hydrogen, okay? So it will be found common product. That's all. This also has gone. Then we remain with, we have this one plus the water molecules. I forgot the water molecules. We have 4 water molecules there and we have 5 there. It means we remain only with the 1 water molecules this side. Then this side it will be cancelled, everything. So it will remain like that. Then this one we have written will remain with, we have 5. Then plus this, now it remains, it's 2 hydrogens, okay? That's all. So this means that by the presence of this ion hydrogen, it means we are in an acidic environment. So if you are to add again in basic, you add hydroxide and you see it will change. we'll add 2 more steps to reach this stage. Now try this one. Try this one and send the solution to, and I confirm, then I'll help you further if you make any mistake. So send solution to 0964 122 411 on WhatsApp. If you don't do this, I'm free to mark you, stuff like that. If you don't do, it's up to you. So try that, please. Just try. Try okay to reach at acidic point. Then I'll conclude with you at basic point. So now what we are trying to say now, we are trying to define state Boy's law, Charles' law, and Avogadro's law. Sketch a simple graph. So Boy's law states that volume is inversely proportional to its pressure. Okay. So this means that we can have V is equal to K1 over P, which is just V varies as K over P. Okay. Then constant is constant, meaning that we can multiply that will be Vp is giving us constant. At different condition, we can still have V1, again P1, then P2, V2, like that. That's the reason why Boy's law will be given by the equation V2, no, V1, P1, stuff like that. That's what I'm trying to say. So Boy's law, okay, to be given as V1 P1 is equals to V2 P1 P2. So this will be the governing equation. So we are saying it's inversely. So the graph that will be for this one, it will be actually like this. So pressure there, then volume. So that's a graph you give for Boy's law. So it states that at constant temperature, we need to keep temperature constant. The volume at constant temperature, the mass of a gas is actually the volume of a dry mass of a gas. What I'm trying to say is at constant temperature, okay? So for a fixed mass of a gas, at constant temperature, the volume is inversely proportional to its pressure, to the pressure. That's what I'm trying to say. So you say at constant temperature, for a fixed mass of a gas or for a gas, the volume is inversely proportional to its pressure. That's all. That's how you define. You can write somewhere. At constant temperature, the volume of a gas is inversely proportional to its pressure. That is it for Boy's law. The graph looks like this. Hope that is clear. Then coming to Charles' law, Charles' law states that at constant pressure, the volume of a gas is directly proportional to its temperature. It means temperature and volume, they are now direct proportion. Even the graph will be direct, like a gradient graph. Okay. So we are saying for Charles' law, it states that at constant pressure, okay, the volume is direct proportional to what? To its temperature. Okay. That means that if there is always a K produced, so we say volume is equals to TK, dividing throughout by T because we want K. So that will be K is equals to volume over T. All right. So K is constant. So we can produce many more V over T at different K. So what I'm trying to say is V1 T1 is equals to V2 T2. So this will be the governing equation. So since this thing is direct proportional, so the graph can look like this. Okay. Is that as the volume increases, also the temperature what? Increases. So at constant pressure, don't forget this, please. So you say for a fixed mass of a dry gas at constant pressure, the volume of a gas is direct proportional to its what? Temperature. That's what you can define looking at the graph. Then Avogadro's constant, Avogadro's law. This one is also a constant graph. I mean a direct proportional graph. So you can hope you have written something, otherwise I'm lagging. So what we are trying to say is, for this one, it states that at constant temperature and pressure, okay, the volume of a gas or equal volume of gases have equal volume of moles, okay. So equal volume of gases have equal volume, equal moles. That's all. Equal volume has equal moles. That's all. That's how you can divide. So for a fixed mass of a dry gas at constant temperature and pressure, it has volume. The volumes are equal to the number of moles. That's all. That's what you can say. Or equal volumes, equal volume of gases or molecules have equal number of moles. That's what you can say. Is that hard? At constant temperature and pressure, okay, equal volumes of gases have equal number of moles. That's all. The graph, it's equal, so it's direct proportion. So the graph will also look like for Charles law. So like that. So number of volume of gases or molecules, same number of moles. Was that hard? No. Okay. I'm sick. So that is it. So now let's go to the calculation part. So the first one says measuring is one of the way of obtaining data in science. Yes, it's true. As scientists, we do this. Explain why it is important to take replicates or replicate measurements in science. Why do we have to replicate a measurement? Suppose we have found that the length of this tire is 20 meters, whatever. Why do we have to repeat and take replicates? One, the reason is, one, we can do this because we want to check the precision, the consistency of our measurement. Is it good that we can use to calibrate other measurements or instruments, because it has been giving us the light and collect data? So we do that for precision. Precision is about, okay, consistent in our data or results. Then the other point that we can give is to reduce error impact. Like suppose we were getting errors, okay? Let's say the first record we recorded is 10, then in the second we got 10.1, in the third again 10.1. It means that we go now again another record replicate to get 10. It means we'll see the error that was actually found. So we could maybe clean the instrument. That's it. So why we do that. So the second reason is to check error impacts. Okay, error impact. That's what I can say. That's the reason of replicating our measurements. Then the other point that I can give you just to support is also to increase the confidence in our data. Confidence in our data. Okay, so this means that we can also do this for statistical analysis. We are here to actually do standard deviation because we got what is exactly, or we could get some replicates of precision. In short, the precision was maintained, that measurement, like a degree of following each other, showing up the same. So that is it. Those are the reasons why we do replicates. The following values 2.3 shan and 23.10 centimeter convey different information. Yes, it's true. Explain the importance of it. So when you see this, it means that we have 0.0, 0.1. Okay, precision, it means how things were getting close to each other. They were getting close to each other by what? 0.1 difference. You get? So this one indicate precision of 0.1. That's all. All right, is that okay? So it indicates the precision of 0.1. What about this one, the other one? This one, it includes the accuracy of, so say here I'll get, so what we do is you get 0 point, here you match the numbers the way they are. So say 0.01, okay? So this is the accuracy, the precision. This communicate the precision. There was a precision of 0.01. Here there was a precision of 1. So that's precision is about how measurements were getting close to each other. So that was the communication, the information we could get from this. That's the importance, okay? The importance of this, we could see the precision that was actually that. So perform the shown mathematical whatever. So when you multiply this, just follow the least significant figure. So when you punch that on your calculator, for me it's giving me 32.3492. So you follow the least significant figure. So here it will be just 32 because we had two significant figures there. You have seen? So just put 32 there. By the way, it was centimeter, so it will be centimeter squared. Then here we are adding all these there in kgs, okay? Even here, what will happen is that we'll follow the list. Here we follow the list also. We can see the list is having 1 there, right? We don't care of the number that will be formed there. So when you add that, it's giving you 104.842 kg. So you follow the list. The list we had is 1 after a decimal point when you're adding. So you say 104.8, okay? Because of 1 which was there, I will put this. That's what we do for addition and subtraction. Okay. So for multiplication, you just follow the number of a significant figure like that. Hope this is sweet for you. This is nice and sweet. Okay. So if we are talking, what mass of sulfuric acid is there in 44.4 liters or milliliters of solution of density 1.58 grams per meter liquid, liters per per millimeters. I'm sorry, I'm tired. This is Rohan. So which contain 90. So they have specified now with the mass that we get, we need to express in this form of percent, which is 96, and get a value. Okay, they have specified. So what we need to do is we need to say density now is equals to mass over volume. Sometimes density can be written as sleeping P. So then it means the mass that we are interested in to be volume times density. So the volume is now 44.4 times the density. You see, even the units will cancel. Don't worry, I won't include them, but I know they will cancel. So here we have the density as 1.85. Okay, so you see that this is milliliters, then there have grams, then milliliters. So the milliliter and the milliliter, they will go. So in short, that's what I was trying to say. So the value that we let me punch. So we're getting 82.14 grams. So this means that we now express in the percentage form. So say 82.14 grams times the same percent they have expressed there, 96 point over 100. Okay, so when you punch that now, it's giving me 78.9. So 78.9 grams. Okay, so this is the answer you needed to write as the mass of sulfuric acid. Okay, so that's how you were supposed to write. Okay, so the other thing that we'll do now is we'll convert this one. This is very simple and sweet. So what we are going to do is we'll use the chain. I'll use the chain conversion, or you can choose, but I prefer chain. So 30 kilometer. So I'll say per hour. Okay, so I'll say for this one I will eliminate by saying 1 kilometer is because they have specified we need to take it into meters. 1 kilometer is equals to 1,000 meters. Okay, so it means this and this has gone. Then times again this hour, I'll say 1 hour, okay, is equals to how many seconds which they want is 3600 like that seconds. Okay, so this and this has gone, have seen, so it will remain with meters per second. So you multiply that will give you, you punch that on your calculator, it will definitely give you 11.7 meters per second. So that's what you are supposed to write. Okay. So it was very nice paper. Alpha got you. Then the where I said you guys should try your best, it's here. It's just that time the video will be very long, so I can't make it. You waste your bundle. You need something like to watch, like, and understand. So for this one is still the same, but in basic. Please, if you feel like, try, and if you feel like, inbox me. The line is here. Thank you very much. And we said now, okay. So everything has been answered now clearly. Thank you for your time. Revise proper and all the best in your exam. Bye. Okay.